Hello everyone, thank you to be here for this talk. Hello also to the people that are watching this talk remotely. So I'm Romain Thomas, I'm security engineer at UL, where I perform security evaluation on mobile banking app. And I enjoy dealing with reverse engineering and obfuscation, mostly for mobile application. And I'm also the author of Leaf, which is a library that can be used to manipulate the executable formats. But today I will talk about SafetyNet, which is a component developed by Google to check the integrity of the device, Android device. And basically, they need to develop that because on Android, you can access to the root privilege quite easily compared to iOS, where you have to somehow find a vulnerability to have a jailbreak. On Android, the system enabled to get root as long as you disable some security feature like the bootloader, the secure boot. So it brings some concern about, for developer, about knowing whether they are running their application on a trusted environment. And that's why Google developed its own solution named SafetyNet, which aims at checking the integrity of the device. So when we talk about integrity, we talk about detecting whether the device has been rooted, whether the system is a custom firmware, or even if it's an emulator. And basically, when you are a developer, you might want to know if you can trust the device on which the application will run, because, for instance, for the video game industry, they don't want to run their game on a device that has been rooted, because maybe it could enable to easily cheat the application. Also in the bank industry, they are not allowed to run the banking app on a device that has been rooted, for instance. And it's not about whether the developer will support rooted device or not. It's a certification that says you can't run the application on a rooted device. So that's why they create a SafetyNet to check the integrity of the Android device, because it's easy to get root on an Android device. So from a developer point of view, you have basically to provide two information. One is the API key of SafetyNet, which is used to authentify the developer. And the other parameter is a nonce, which is used basically to avoid some kind of attack like replay attack. And when the developer provides these two information, it will get the result of the SafetyNet attestation through one callback. I mean, two callback if there is a failure, but mostly one in the case where it's a success. And SafetyNet will provide the information about whether the device can be considered as safe or not. So why doing this talk at Black Hat Asia? So because basically in 2017, there were already a talk at Black Hat Europe about SafetyNet, and Colin and John presented some inner work of how SafetyNet is designed. And they mentioned also a component, DroidGuard, but they did not explain a lot about how it is used and how it works. And by the time, there was also Magisk, which is the routing solution for Android, and that enabled to easily bypass SafetyNet. So it's very well designed, and they find some tricks to basically enable to bypass SafetyNet, like just by enable a setting in the application. So it's very easy to actually, it was actually very easy to bypass SafetyNet thanks to Magisk and Magisk Eye. And Google did some improvement because of this routing solution, where basically they improved SafetyNet with some kind of hardware attestation, which leverage some hardware feature of the device to know whether the bootloader has been unlocked or not, which can be a sign of a rooted device. And SafetyNet will provide two flags basically to determine whether the device is safe or not. The first one is basic integrity, and the second one is CTF profile match. Here are the descriptions that are available on the Google website. But basically, the basic integrity check will determine whether the device is rooted, if it's an emulator, and if there are some presence of API hooking like FRIDA. And on the other hand, CTS profile match will do the same, more or less the same check as basic integrity, but it will also detect if your bootloader is unlocked, which is one step to get root on an Android device. But the important point here is that CTF profile match will be set to false if the device did not pass the Google certification. So it can bring some false positive in the attestation. And back in January of this year, the main developer of Magisk joined Google, and because of some conflict of interest, I guess, he decided to remove Magisk hide from the release 24. So now, in the latest version of Magisk, there is no Magisk hide, and we can't use it to bypass the root detection of SafetyNet and other WASP solutions. So now, if we go back to the snippet that show how to use a SafetyNet from a developer point of view, now from a system perspective, SafetyNet, the developer will trigger a SafetyNet request through the SafetyNet SDK that takes place in the blue area. The SafetyNet SDK will craft a message that will contain basic information about the application that asks for the request. It will forward this information through an intent to GMS core. GMS core on Android is a component that contains all the Google logic on the device. This component, GMS core, will perform some very classical root check on the device. So it will check if, for instance, the SU binary is present. And it will start also to create a protobuf message that will contain the information about the integrity of the device. Then GMS core will call DroidGuard, which is another component that runs in another process, but that is very close in terms of communication, I would say, to GMS core. DroidGuard will perform the heavy check to determine whether your device is safe or not. I mean, if the device has been rooted, if it's an emulator, and so on. So most of the check of SafetyNet are done through DroidGuard. Then DroidGuard will send the result to GMS core that will forward the information to the Google backend, and the Google backend will decide which flag to set to false or true. So here is the protobuf message that is created by GMS core. So in the orange box, you have the basic information about the application that ask for the attestation. You have also some information about the small and easy check root and SE Linux status. So here it's just about Java check, so it's not obfuscated. I mean, you have to reverse the GMS APK, but it's very straightforward to identify. And on the other hand, DroidGuard, the result of DroidGuard will be happen to this message, and it contains a blob of data, what looks like a blob of data, but it actually contains a lot of information about the status of the device. This protobuf message is sent to the Google backend that will do some computation to determine the results of the SafetyNet request. So the goal of this talk is mostly to present DroidGuard, which is a heavy module that contains different layer of obfuscation. And in particular, the non-goal of this talk is not to present a new technique to bypass SafetyNet, because it's not the purpose, it's just to provide a description of how it works. So the question now is how this value generated through DroidGuard is actually generated and what kind of information it contains. So, as I said quickly just before, DroidGuard run in a different process than GMS core. So the name of the process is COM Android Google GMS Unstable, and it's associated with an APK that is located in the data partition of the application. Actually, this APK is dynamically downloaded from the Google server. So it's not an APK that is already installed on the system. It's an APK that is updated every 2 weeks and that contains a small Java layer and a native library written in C++ that implement somehow a VM. And this VM is heavily obfuscated with different layers that I will describe a bit later, and it contains all the logic of the DroidGuard. So just to summarize a bit of the process of DroidGuard. So first, GMS core will trigger an event that will start DroidGuard. Then DroidGuard will run a bytecode provided by the Java layer. So, as I said, DroidGuard implements a VM, and to use the VM, you have to provide a bytecode, and this bytecode is actually downloaded for each attestation. So, DroidGuard starts with a Java layer that it just used to bridge with a native layer that is located in the native library. This native library is obfuscated with MBA, with anti-debug, anti-hooking. All the buffers are encoded. I mean, you have different kind of layer of obfuscation. DroidGuard also download the bytecode for each attestation, which means that each time the developer asks for an attestation, DroidGuard will download a dedicated bytecode for this attestation. So remember, you have this APK that is updated every 2 weeks. And the bytecode running through this VM is downloaded each time for each attestation. And of course, there are some small modifications for each bytecode, which can be difficult to analyze because first, when you reverse the APK, you have to be somehow quick because every 2 weeks it changes. I mean, some part of the VM change, and the bytecode is downloaded each time. Then the bytecode run through the VM. The bytecode contains actually all the checks to determine if it's an emulator, if the device is rooted, if there are some hint about hooking framework and so on. It will also generate the token named DroidGuard. This token will be sent back to the DroidGuard main class in the APK, and then it will be sent to GMS core that will add this value to the protobuf message, and that will be eventually sent to the Google backend. So if we want to understand how SafetyNet works, we basically need to understand how the VM is designed and how the bytecode, what kind of action are done through this bytecode. So it's a 30-minute talk, and it outlines a month of research. So I will just describe some feature of the VM, and you can find more details in the white paper. So basically, the VM is designed with 256 registers that can contain typed value. I mean, a register, it's a virtual register, so it's basically a C++ structure that contains a type and a value. And the type can be a pointer, can be a double, can be a GNI object, it can be also a string, and so on. And for each new version of DroidGuard, they are changing the layout and the ID of this register, which means that basically if you manage to identify that in the version A of DroidGuard, an integer is associated with 1 or 3, in the next version, the integer type will be associated with 1. So that's one of the challenges when reverse engineering DroidGuard. Here is an example that performs a write operation in the VM. So basically here is the function that will just write a value in the VM register. So on the top, you have a mixed Boolean arithmetic expression, which is used basically to encode or to decode a register value. Because in the DroidGuard VM, all the value of the register are encoded, which means that if somehow you manage to dump all the register value, you won't be able to see what value they are actually, because all the value are encoded. And they are encoded through MBA. And the MBA are changing every 2 weeks because of the VM update. So here you have the decoding part of the register value. Then here you have basically the std string destructor, because as I said, DroidGuard is written in C++, and there are some optimizations that are done through std string, and here it's the inlining of the destructor of std string. Here you have on the right-hand side a deallocation of a GNI object, because basically when you want to write a value in a register of the VM, you have to disallocate the previous value. So here they are safely removing the previous value, and then on the bottom you have a MBA that will encode the actual value. So here, just to give you an idea of how it can look like to reverse engineering. So basically in the DroidGuard VM, you have a dedicated handler that can be used to perform syscall, to perform arithmetical operation, to perform GNI call, and so on. And here is a basic block that will initialize the different handlers. So basically they are storing a pointer into the VM object. So now, regarding the execution of the bytecode, you have basically a sequence of VM handlers that are used to perform some computation or some check on the device. So the first handler is used to read, for instance, a register. Then you will resolve a symbol that is associated with a buffer, clock, get time, and so on. And basically, all this sequence is used to detect whether the device is whether the application is under debugging, because basically if you can compute the time between the first call to clock get time and the second call to clock get time, you can determine whether it takes too much time or not. So here you have a sequence of handler, and you have the same, for instance, to detect hooking or to detect root on the device. Now about what kind of check are done to detect root. So once we manage somehow to identify the different handler and to identify how the bytecode works within the VM, we can try to analyze this bytecode. So here is an example of a sequence of the bytecode. So actually it's just a representation. It's from reverse engineering, dynamic analysis, and so on, but basically there is an example where they are checking whether the data local X bin exists. So first, they are calling the read buffer VM handler that decode the string data local X bin, and then they are calling the call function handler that will be used to perform a syscall associated with faccess@. So actually, faccess@ is not hard-coded in the VM. It's just results of the execution of the bytecode. So among the different checks to detect if it's a rooted device, we have the classical one, so data local, TMP, SU, and so on. So nothing very fancy, I would say, on this point. Same, you have some system property check, so it's just some strings that we can identify. And basically to determine whether there are some presence of API hooking, they are checking if some libraries are present in the memory space of DroidGuard. So here is an example where they are checking if libriru id expose is present. So you have the same for Frida agent, for lip send hook, and so on. But the interesting point that I found when reverse engineering this bytecode is that basically they are also able to detect whether the device has been infected with Pegasus. So there is some kind of IOC to detect if there are some presence of Pegasus, which can be quite weird because it's not like the normal way of routing a device, but they are able to detect it. In addition to this check, they are doing some kind of telemetry to collect information about the device and about the environment, and to send this information to the Google backend that will perform some advanced check based on this information. So it's a kind of trade-off to find between checking if, for instance, this library are present during the execution, where you get basically a Boolean value, true or false, and collecting information about the environment of the device. So they are collecting information about, for instance, the zygote process. They are collecting information about system properties related to the bootloader. They are also collecting information about kernel info and so on. But they need to find a trade-off between collecting everything, which can cost a lot of data to send, and doing Boolean check that can be somehow easy to bypass, because basically if you manage to bypass the syscall, that's done. So here you don't know actually how it is really used in the Google backend to determine the basic integrity and the TTS profile match. So here is another list of information. On the top here, you have also the certificate chain that is used to perform the hardware attestation. So the hardware attestation is not something very magic in SafetyNet. It's come from public APIs that developer can also use. And they are basically sending the whole certification chain to the Google backend that check that the chain is valid and has not been corrupted, and that the bootloader is locked or not. So to summarize, DroidGuard collect different information about the device by running a dedicated bytecode in a VM that is updated every 2 weeks. And this final token is composed from Boolean checks that verify whether this file is present or not, or if the library is present in memory or not, and from telemetry data that basically are a collection of information about the device. And you don't know exactly how it is used by the Google backend to check the integrity of the device. So actually, SafetyNet and use a design based on a VM and a bytecode. But actually, Google used this design to run different kind of bytecode. So when I analyze SafetyNet, I was focused on a bytecode that aim at checking the integrity of the device, but they are also able to run a dedicated bytecode, for instance, to check during the device enrollment with your Google account whether you are a bot or not, for instance. And there are different bytecode dedicated for different action on the device. So DroidGuard provide all the design to run Google bytecode on your device with different layer of obfuscation. Now, one question is, how much, what is the cost of this kind of reverse engineering? So definitely is very difficult, and I took several months to do it, so I won't say it's very easy and it's just a matter of 2 days. No, it takes months, and you have to deal with the update, you have to deal with different layer of obfuscation, so it's not very easy. And so I had to develop some tools to do that. I also use a public tool like QBDL for simplifying the MBA. I also use MSynth that is very efficient for simplifying the MBA. And I also developed some dedicated tool, for instance, to do some kind of code lifting. So instead of reverse engineering a complex function, I just extract the piece of code that I were interested in, and I just run it outside of DroidGuard. And doing so, I did not have to reverse every instruction. Basically, I just have to run the correct piece of code. So in terms of how many days, weeks, or months it takes, so I did that on my spare time during weekend and quite early in the morning. But if I would have to give a number of weeks, I would say that just to get an overview of the VM and to be able to play with the bytecode, it took me more or less 5 weeks. And on the top of that, you can add 2 weeks for developing your toolset. And then once you have everything ready, in the end, I managed to reverse a new version of the VM in a couple of hours. So SafetyNet is well designed, well protected, and it's difficult to reverse. But I managed to bypass the basic integrity flag without Magisk hide. Regarding the CTF profile, it involves the bootloader status, and it was out of scope of my research. But now, what are the limits of the design of SafetyNet? First off, DroidGuard runs in a dedicated process that is different from the application that asks for the request. Which means that when they are saying that they are able to detect API hooking, that's true, but that's only true in the process of DroidGuard. They are not able to detect, for instance, if an attacker is running FRIDA in the app developer. So all the checks are done in a dedicated process that is different from the original process of the application. That's why when you are enabling Magisk hide, you just have to target 2 processes to bypass SafetyNet. The first one is GMS core, and the second one is the one that ends with unstable, and that is actually DroidGuard. And that's these 2 processes that needs to be targeted, because actually DroidGuard does not check the integrity of the original process. They are doing all the check within the dedicated process associated with DroidGuard. So just, there are some kind of Easter eggs when you are reverse engineering the bytecode, which are associated with DroidGuard hello, and you have fancy message. But basically, if you are, the ID after the email is unique, so it means that each time you are running the bytecode, there is a different email address, which means that they will be able to identify your device when you send an email to this address. So that's why I actually did not send an email to this address email, even though I contacted Google to share this different research. Last word about the hardware attestation. So actually, as I said at the beginning, Google introduced hardware attestation to improve the way of how SafetyNet works, because basically otherwise it can be more or less easy to bypass. And actually hardware attestation is nothing, it's not something magic. It's just this kind of code that is running through the different handler of the VM. But in the end, the important point is keystore get certificate chain, which return a certificate chain that is likely signed by a trusted component, and more precisely trust zone, that contains the status of the bootloader. So the status of the bootloader is signed on the hardware part and is actually collected through get certificate chain that is a part of the telemetry data. So thank you for your attention. I uploaded some samples of the VM and the bytecode on GitHub. And now I would be very happy to answer your question if you have some. Thank you.